All right, welcome back. Imagine that we have a snare drum. All right, Murph. Murphy's barking here. A snare drum, and so that's a very thin membrane that's stretched over a ring, and so it can come down here, and there's kind of a clamp that goes around the edge here to keep that tight. And typically on a snare drum, there's little screws that you can use all the way around to tighten or loosen that membrane. And what that does is it basically tunes the pitch of the drum. Looking top down on that drum would be a circle. And if I was to hit the top of that drum at some location, then that would initiate some sort of vibrations and the vibrations would be satisfying in much the same way that a string under tension does. It would satisfy the wave equation, except now we are in 2D. So here we'd have the wave equation, but the vibrations are moving both in the x and the y direction. So our wave equation becomes UTT is equal to, instead of c squared uxx plus uyy. Now if you wanted to solve this thing right here, on the circle representing our little snare drum there, you might expect you would move into polar coordinates. And in that way, we could represent the boundary of that as a single value of r equals, let's say, a. And then you might say that the solution at r equals a is equal to probably 0 in this case. Makes sense. If you did that, and then you went and walked down the path a little bit of the solution, you would end up obtaining some differential equations, which would be Bessel differential equations. These things have a regular singular point. You might remember this is one of the last topics of differential equations where we use series solutions around regular singular points to obtain solutions. And you can do that, series solution, but I'm telling you right now, this conversion to polar coordinates, the move into Bessel differential equations, and then to do the series expansion, get the solution, get back into your full PDE solution, that's a bit of a go. And time constraints are going to suggest maybe this is not the best use of our time, but nevertheless, we do want to see what happens when we have a time-dependent process in 2 dimensions. So what's the save here? How can we save ourselves a bit of work? Well, instead of a circular drum, we're going to have a rectangular drum, like this. Okay, same thing. I have some membrane that's stretched over this rectangular drum, and all along the edge, it's clamped to keep it tight, like so. And thus, on the surface here, we're going to have vibrations once we hit the drum, and the vibrations are going to be governed by this 2-dimensional wave equation right there. And then on the boundaries, we're just going to make it 0 on each boundary. Now U represents the displacement of this membrane in both x and y, and also time, at any given location. And so it can be positive if it's above equilibrium, or negative if it's below. And so U equaling 0 is just indicating that equilibrium height that we're fixing the edge of the membrane to. All right. Now, what is the c squared here? Just like in the one-dimensional string, c squared, when you derive it all out for 2D, nothing much really changes. It's still equal to tau over rho, tau being the tension, technically the tension per unit length, and rho is equal to the mass density of the material per unit length as well. So Yeah, it's basically just the two-dimensional analog in every way you might imagine it to our one-dimensional wave equation. Okay, of course, I could write it as UTT is equal to c squared grad squared u if you want to. That's the Laplacian operator, of course. Okay, I'd like to be a little bit more precise now about my boundary. And so in this rectangle, I'm going to label this point, well, let's draw it again, actually. So let's draw it down here. UTT is c squared grad squared u. This is 0, 0. This is the point A, B. So down here I have, right over here, let's say, u of 0, y, and t is equal to 0. U of a, y, and t equals 0. U of x, 0, and t is 0. U of x, b, and t equals 0. So homogeneous Dirichlet boundary conditions all the way around this rectangular drumhead. Okay. What else do we have? Well, now we have initial conditions. Which we didn't have lately because we've been solving Laplace's equation and Poisson's equation, both of which are time independent, so we don't have initial conditions. Now we might have something like generically u of x, y when t is equal to 0 is some initial deflection or displacement of this drumhead. Now, in reality, this is just uniformly 0 everywhere because the drumhead is just going to be flat upon initial strike. But possibly you could imagine a situation, possibly maybe not a drum, but some other vibrational situation where you might have some f of xy. Secondly, we need the u sub t, the time derivative, because we've got a second order in time PDE. So this might be some other thing. Now this would be the initial velocity we might strike the head at. So you got your drumstick and you whack it somewhere, and that's going to initiate these vibrations, which in turn produce sound. Okay. Now both of these are in the domain D, from x 0 to a and y 0 to b. All right. How do we solve this? We've only got one way. Let's try separation of variables. And what do we do if there are three terms, x, y, and t? Well, we just load them all up. So we seek non-trivial solutions of the form the displacement, a function of x, y, and t, is equal to some capital X, the space component in x, then the spatial component in y, and then the time component, capital T. So it's assuming a separated form as such, and we simply plug into the PDE, into that two-dimensional wave equation. And of course, all the derivatives land on the specific part of the separated solution and thus slowly forms a set of ODEs. So can't get ahead of ourselves here. UTT would give me x, y, t double prime equals c squared uxx, so that's x double prime yt, plus u sub yy would be x y double prime t. Okay, what I'm going to do is divide both sides by c squared xyt. And what that's going to give me is t double prime. The x and the y are gone. I'm going to gain a c squared over here. And there's also a t on the bottom right there. And this is equal to, c squared is gone. I have an x double prime over x and a y double prime over y. Well, this feels familiar. Function of time, t. Not a function of time. Okay, it's a function of x and y. And if they're equal to one another, of course, they must equal at most a constant. So I'm going to introduce our good old friend lambda, the separation constant. All right. Now, if I link the last and the first together, I obtain 1 ODE for t double prime. If I multiply up by tc squared, I get equals lambda c squared t, or t double prime minus c squared lambda t equals 0. All right, so there's 1 ODE, not a particularly challenging one either. You might imagine sines and coses coming out of that, but we won't get ahead of ourselves here. I still want to keep mining other observations out of this relationship up here. All right, so the next thing I'm going to do from this is just take the latter two parts of this, the x double prime over x plus y double prime over y, and then the lambda. Okay, and I just want to rearrange that slightly into x double prime over x equals, and I'll write this as negative y double prime over y plus lambda. And we can have a very similar conclusion here. This part is a function of little x. This part, there's a constant in there, but it's at most a function of little y. And so similarly, these two must be equal to, at most, some constant, some separation constant. I've already used lambda, so I'm going to introduce a new separation constant, mu. So let's give that a name. It's a separation constant. And so I can take the mu, and I can take the x, and I can rewrite this as x double prime, multiply up by x. Okay, so this x is going to come up here on the mu, and then I subtract it off to obtain my ODE as x double prime minus mu capital X equals 0. And finally, if I look at these two, and let's drag it down here maybe, looking at those two and rewriting that, I get negative y double prime over y equals mu minus lambda, or y double prime over y equals lambda minus mu. And so y double prime is equal to lambda minus mu y. Just for notational ease, I'm going to introduce a new variable, nu, which is the lambda minus mu. And if I write that as such, I get y double prime minus nu y equals 0. A third differential equation. All right, so there's the first one in t, there's the second one in x, and the third one in y. All right, up next, boundary conditions. Let me get a new sheet going here. To it for a sec. T is set up here, bang right here, with a lambda. Now I just got expressions for nu and mu, and so what I'm going to do is go down here and use this equation, rearrange it slightly such that the sum of nu and mu is equal to my lambda, and I have expressions for that and for that, so obviously I can get an expression for lambda. Okay, so a sec. Here's the ODEs. Now typically we might have like an x double prime plus lambda x equals 0. We dealt with that a lot. And then lambda was typically positive, giving us these sign solutions. Just because of the way I've written this, these separation constants in this particular case, it now turns into a minus mu and a minus nu for the y solution here. And basically all that means is that our values are negative of our usual sense. Slide. And look at this expression here. I have lambda minus mu equals nu. So I can rearrange that and say lambda equals nu plus mu. And so if I have these two, the mu and nu, then I can get lambda. Pretty easy. All right, so let's take one of the boundaries. Let's say u of 0, y and t equals 0. And if I plug that into my separated solution, I get x is 0, y and t are just unrestrained, let's say. Okay, y is between 0 and b. T is positive in all of these here. So of course, if we don't want to make y uniformly 0 or t uniformly 0, thus giving us only a trivial expression for u, then the only remaining part here is that x of 0 is equal to 0 to obtain a non-trivial solution. Okay, and so if we perform the same analysis, we would find that x at a is equal to 0, and then y of 0 is going to be 0, and y of b equals 0. All works the same way. Of course, there's no boundary conditions on t. The boundary conditions only exist on the x and the y components of the separated solution. All right. So x of 0 is 0, x of a is equal to 0, and then the same thing for y. These are just your basic good old eigenvalue problems with homogeneous Dirichlet boundary conditions. We don't need to do the whole search through all the positive, 0, and negative potentialities for the eigenvalues. Let's jump right to it. I'm going to call xm of x the x solutions, which are sine functions, you might remember. And the form of these is an m pi x over a, such that that equals 0 when x equals a from the boundary condition. And m here is 1, 2, 3, and so on. And then similarly, y n of x is sine n pi y over b. N is equal to 1, 2, 3, and so on. Now, the separation constants here, there's a tiny detail I want to bring your attention to. So let's go over here, these separation constants. Mu is equal to negative m pi over a squared, and then nu is equal to negative n pi over b squared. right, so now we go to the t equation. And just to remind you, pull it off the other slide, it's t double prime minus c squared lambda t equals 0. Now I have an expression for mu and nu just above there from solving out those particular little problems. What is lambda? Well, I can go back to the... All right, so I know what the lambda values are. It's mu plus nu, which is negative m pi over a squared plus n pi over b squared. Now the two negatives, in the one in lambda and then the one actually in the ODE here, right here, that would cancel and give you a positive value. So when you put it all together here, you get, you get t double prime plus c squared m pi over a squared plus n pi over b squared t equals 0. All right, so the second derivative has to be negative of the original function in order for this one to work, and of course that admits sines and cosines. I'm going to note that this ODE has a different solution depending on the value of m and n. And so I'm going to write the solution form as like a t sub mn. And if I vary one or the other, then I obtain a slightly different ODE. What do I get? Well, I get some constant in front of the cos and a constant in front of the sine. So I'm going to write this as bmn cos root lambda mnct plus cmn sine root lambda mnct, where I'm using the notation now lambda mn is this m pi over a squared plus n pi over b squared. Now these root lambda mnc terms which is equal to c, the root m pi over a squared plus n pi over b squared, or c pi root m squared over a squared plus n squared over b squared. These things are called the characteristic frequencies. Well, we've got all the components. We've got our x and our y and our t. So finally we take all this and we multiply it all together. And so we then get our u, which I'm going to subscript with mn, because now we have these combinations of the m and the n values that admit different solutions that we're to superimpose. So u mn x, y, and t is equal to x m of x, y n of y, t m n of t is equal to sine m pi x over a sine n pi y over b, and then finally this t solution up there, which is the bmn cos root lambda mnct plus cmn sine root lambda mnct. And there we have it. Now, of course, the final solution is a superposition of all these umn solutions. Okay, so finally, u of x and y and t is equal to the superposition of all of these particular umn terms, and so we're going to have a double sum m equals 1 to infinity, n equals 1 to infinity of the umn of x, y, and t as written right above there. All right, so the only thing that's left is the initial conditions, which in turn should hopefully determine my coefficients bmn and cmn. All right, so let's go on to the initial conditions and see what we get. If you remember, originally I had some u of x, y, and 0 being defined as some function f of x, y, and I said, you know, if it's a drum, normally f is 0 initially, but you know, it could be something in some context. And so what do we get when we plug this in? We have, again, the double sum m equals 1 to infinity, n equals 1 to infinity, t is equal to 0, so that's obviously going to make the, if we look up here, the sine terms are going to be gone. Cos of 0 is going to be 1, and so I end up with a bmn, and then my sine terms, sine m pi x over a, sine n pi y over b. I'll do the other one as well. So my g of x, y was my time derivative of u, evaluated at t equals 0. And I'll do this in 2 steps. I need the time derivative, so that's obviously just going to impact up here. So the cos is going to turn into a minus sign, the sine will turn into a cos up here, and the chain rule is going to give me the root lambda m n c term popping out. All right, so I would get sum m equals 1 to infinity, the sum n equals 1 to infinity, sine m pi x over a, sine n pi y over b. And the first term is going to be gone. The bmn turns into a minus sign evaluated at 0, 0. So I'm going to get c, the root lambda mn. It's going to be a cos term in there. I'll put the cmn's in here, and then cos of 0 will be 1. So I get this expression. Now, this is basically the setup we've seen previously for our double Fourier sine series expression for a function f, or in this case g. And the only difference here is that I have an extra little constant term here. That just gets divided through, no big problem at all. All right, and so I can use that result of the double Fourier expansion of a function f of x, y straight away and obtain these coefficient expressions. So the bmn's is equal to, remember we had this 4 over ab, and then the double integral 0 to a, 0 to b. F of x, y, sine m pi x over a, sine n pi y over b, dy dx. And then the cmn, very similarly, is going to be 4 over a, b, c root lambda mn, double integral. Sorry, that's a 0 down here, up to a, integral 0 up to b, g of xy, 2 sine functions, m pi x over a, sine n pi y over b, dy dx. All right, so we'll give these a little box here. There, and there's the C. And that does the complete solution for the wave equation on a rectangular domain. Of course, if f is 0, the BMNs all disappear, and then we just have our initial velocity, initial velocity that we hit the drum with. That's going to be contained in the g of xy, some little bump at some xy location, and then you have a little integral to work out here to get your c's. Throw them in there, and right back up to here is your full solution. There you have it.